So here we are yet again for another lovely session of MENG 3310 Fluid Mechanics. This is going to be the 26th lecture in the video series, and today we're going to continue with a discussion on similitude, an introduction to similitude. This is actually, I'm doing a second portion of a lecture today. I just wanted to cover two different topics and decided to divide them up into two different videos. Okay, so let us consider similitude. This is in 7.8 and 7.6 of the Munson text, so let us consider. I want to describe the need and benefits of similitude in fluid mechanics, describe the common variables and dimensionless groups used for creating models, and finally apply the principles of modeling and similitude. So let us look at similitude. This is where dimensional analysis gets very interesting. So fundamentally, what it means is resemblance. The word similitude means resemblance, a similarity. So it means resemblance. In other words, one thing is similar to another. I want one thing that is similar to another thing, or analogous. This is necessary for many designs. In other words, for example, if you want to use a wind tunnel, imagine a wind tunnel. What is the idea of a wind tunnel is that you're going to test something at scale. Now the problem is things don't necessarily scale linearly. Like in other words, like if you cut the size of the aircraft if you build a scale model of an aircraft to 1/10, well, the viscosity doesn't magically decrease to 1/10 either. So it gets really complicated. Or what happens if I want to model the movement of a ship, but I have a wind tunnel and not a water chamber, or not a wave tank or something like that? How do I do that? Is there some way I can use a wind tunnel to model the behavior of a ship? It turns out there is, but you need to use something called similitude. So we need to look at how what we're really looking at is how things scale and how one change in one variable will affect another variable. And what this comes down to is fluids behave differently at different scales. Fluids behave differently at different scales. And the best example of this that I can ever think of is insects. Have you ever thought about the design of insects? Like, I don't know, any kind of fly or any kind of butterfly or the humble mosquito or anything like that? Have you ever thought about the design of an insect from a mechanical point of view? Think about this. Well, I'm going to draw an insect and I'm not going to draw it very well. So I can draw the right number of legs. 6 legs. We got the abdomen, the thorax, if I can remember back to my 3rd grade. So this is my little ant here, or whatever it is. This is my insect. But what do you notice about their mouth parts? They always have this long part. Do you remember what that's called? Proboscis. Yes, if you remember from your elementary school biology class, right? Proboscis. You ever wondered why they have that? You ever seen a mammal with a proboscis? I mean, yeah, you have elephants, but those are more evolved for gripping objects, not for just drinking. Why the heck does that? I mean, why can't the ant just have a mouth and just reach down and drink directly from a pool of water?
You might get stuck or something.
You might get. You might get. Someone said you might get stuck. You might get stuck. Life for an insect is very dangerous. Well, not only getting squished, but life for an insect is very dangerous. Taking a drink of water is a potentially fatal event. And the reason is surface tension. Example is surface tension. Surface tension. So you can think of this as every time you get out of the bath or the shower, there is a thin layer of liquid, a fraction of an inch layer of liquid on you. Now, if you are a human, if you're a crudely drawn human, like A very crudely drawn human.
Very avant-garde.
Looks like a what? Like a Christmas cookie, yes. You're going to have this thin layer of water on your surface, right? And if you actually go and measure the weight of that, you might find it's only a pound. You might find it's a pound or two, which is, it's a non-trivial amount of water, even for, it's not, Now, to actually lift yourself out of the bathtub, if you can lift yourself out of the bathtub, if you're not, infirm or something like that, the added extra pound isn't really going to do much to impede you getting out of the bathtub. But if you figure out if you multiply the surface area of a human times whatever fraction of an inch that layer of water that's clinging to, you might actually find it's a pound or two of water. But that is a small overall portion. That is small compared to your body weight. You're talking about, you're adding less than 1% to your body weight. But what about an insect? If we go back to that insect and look at it to scale, that crudely drawn insect, oh boy, it might end up being something like this. So this the thorax and the head with the antenna and things like that. If it goes for a swim for some reason because it wants to die, it might end up, that little layer of water now looks like this. It's going to be, it may be completely enveloped by the water. And this is done by this is a property of surface tension. Water likes to cling to things. And what is a thin layer of water on a human being is enough to completely surround the insect. A insect, if it's not careful, it can get sucked into a puddle and drown while trying to get a drink of water. If it's stuck like this, it's not getting out. It is going to die. I mean, it's going to die from it. Ants and butterflies and everything else need air just like we do. They don't have lungs, but they have other mechanisms. But they need air just like we do. And if you put an ant in a vacuum chamber, it's not going to fare very well. But anyway, although if you want to put some roaches or mosquitoes in the vacuum chamber or in a vacuum chamber, I would not object. Anyway. So that is a simple example of how fluids can behave radically differently depending on your scale. So if you're talking about fluid viscosity, for an insect, for a flying insect, the viscosity of air is like trying to swim through syrup. It really is, relatively speaking. For a bird, flying through the air is more similar to, the viscosity of it relatively is like swimming through water. For a human to try to fly through air, we need a big plane to do so because it's like, flying through air for us. You learned in this class that flying through air is like flying through air. So let's say we had something like this, where pi 1 is some phi of pi 2, pi 3, pi 4, etc. And we want to know what dimensionless parameter is most important to describe the system. So to do this, we need to select one particular pi term. What dimensionless parameter? So we have to ask ourselves, what dimensionless parameter is most important to describe the system? Is most important to describe the system. Describe the system. Okay, so to do this, we must use similitude. In other words, they have to mesh. Pi 1, now I'm going to use pi 1m and pi 1p. This is going to be the model and the prototype. The different pi's must be equal. So pi 1m, pi 2m, and pi 3m, if we had, say, 3 pi terms. The way we balance our system is to make the pi terms equal. Here, and I'll put some notes on this. So I'll have 2 sets of pi terms. One would be for the model, the scale model, and the other, I got that backwards, sorry about that. All of those should have p on them. Pi 2p, pi 3p. And these refer to p, which is the prototype. or the full scale model? The real or prototype? Full scale. Full scale. Okay. Scale, what do I mean by scale? Well, scale is referring to separating variables. When we're looking at scale, we may need to separate out the individual pi terms, need to separate out each variable. So you might have something like lambda being your scale factor, where lambda perhaps could be equal to, for example, in one case, Lm over Lp, where Lm would be your model, maybe the length of the model, and Lp would be the prototype or the real. The real or the prototype. And I want to then look at a list of some common pi terms. So maybe I'll do that on the next slide. So I think I'm going to switch here really quick. I want to look at some common pi terms. So often we'll select these as our pi term that we'll use for scaling, because these are very common ones that tend to really determine, they just show up again and again in experimental analysis. And some of these you may have heard of, and some of these you will hear of later in the course. So you'll have something like, let me list a few of them. Reynolds number. Reynolds number, which I'm going to abbreviate RE. The Froude number. So I'm just going to list them, then I'm going to list the formula for them, and then describing what they're usually used for. The Froude number, FR, the Cauchy number, or the Cauchy number, CA, the Weber number. So there are a lot of common numbers that are used in fluid mechanics experimental design. So the fluid number, the Weber number, WE, or one you've probably heard of, the Mach number, which would be which is often abbreviated MA. And the formula in each of these are dimensionless, so they are pi terms. And this might be something like rho v LD over mu, VLD over mu, or VLD over nu. And this is just used in general fluid, so this is used generally in fluid dynamics. The Reynolds number is. The Froude number is equal to V divided by the square root of GL. GL. And this is used for open channel flow. Things like canals and flow along a free surface, basically. Open channel flow. We don't usually cover that in the mechanical engineering, fluid mechanics, but in the civil engineering fluid mechanics, we spend a good bit of time talking about that. For obvious reasons. A lot of the things that civil engineers do are open channel flow, things like drainage ditches, things like culverts, things like canals, that kind of thing. Things civil engineers learn about. The Cauchy number is rho v squared over EV, a modulus. And this is for a compressible flow, so that would be the modulus elasticity of your fluid. For compressible fluids, or compressible flow, where the slight compressibility of fluids is important, the Weber number would be rho LV squared over sigma, and this would be problems involving a surface, involving a surface. And finally, the Mach number is V over C. Now, c is not the speed of light. C would be that would be quite ridiculous, but for fluid mechanics anyway. But c in this case is the speed of sound at say air at a given pressure and temperature. So, if you've probably heard of this in Chuck Yeager breaking the sound barrier through history class or something like that. And often we talk about, say, the capabilities of high-performance fighter planes and stuff like, and those kind of things, or rocket engines and rocket systems, things like that, discussing what kind of Mach number they're capable of flying at. So we'll say a plane is capable of steady flight at Mach 2 or or can engage its afterburners and temporarily engage it, it can temporarily fly at Mach 3 or something like that. We use Mach numbers as a shorthand for velocity in many cases, but it is used for compressible fluid flow, especially high velocity fluid flow. Okay, so let me actually work through a couple examples describing how to work with these. So let's look at one example here. So let us say that I have so this is the kind of similitude problem we might have. Let me consider this. Okay, so example here. So given, say the prototype, say we have a prototype, and I have a model where the system is like this. I have a diameter, the d on the prototype, dp is equal to 3 meters. So I'm looking at something that my prototype is going to be 3 meters wide, and then I'm going to be looking at, but then in the model, or for the actual, for my actual object, is going to be 3 meters wide. And then in the model, I'm going to be using fluid flow of 2 meters per second and an object that is 100 millimeters wide. So instead of modeling something that is, building something that is 3 meters wide, which would be quite long, I can instead use something like something that's only 10 centimeters long, or much easier to work with. And I want to find the velocity of the prototype, or the real thing, using Froude symmetry. And really, all we're doing is setting one Froude number equal to the other. So this one's fairly straightforward. Solution, well, the Froude number is going to be equal to V over square root of GL. And then here, actually, you know what? I mislabeled this a bit. This should not be diameter. This should be length or sometimes diameter or diameter. You're never going to have both of them at the same time. Sorry about that. Length or diameter, depending on the context of your system. Okay, so this here, what I'm going to do is I'm going to set the two Froude numbers equal to each other. So I'm going to say Froude number of prototype is equal to Froude number of the model. And so V divided by the square root of GL for the model is going to be equal to V divided by the square root of GL for the prototype. And if I then go and solve this for VP, the velocity of the prototype, I get Vm times the square root of GP dP over GM dm. However, g is the acceleration due to gravity. It's going to be constant. So this is just the this is just Vm times the square root of the difference in the diameters, or the ratio of the diameters, dp divided by dm. We have that. So then finally I can go, okay, here, I can just plug in the numbers. If I plug in this here, I can find that VP is equal to VM, 2 meters per second, times the square root of 2 meters divided by 0.1 meter, and I'll get that that the actual prototype would have a velocity of 11 meters per second. So in other words, I am saying that a system or a model that is 100 millimeters wide and has a velocity of 2 meters per second is experimentally equivalent to an object that is 3 meters wide and has a velocity of 11 meters per second if I'm using fluid symmetry to describe the problem. And then I think I'll have one more problem that I'll work through. Here's just my second example, and then we'll be done. A little bit late today, but that will be okay, hopefully. So then example 2. Let's say I have a model submarine, and I want to use this to model a real submarine. Model submarine at 1/15th scale. And let's compare the model to the prototype. So I'm given the following information and prototype. So I want to design a submarine or run some analysis on a submarine, but it's expensive to actually build the submarine, so I want to build the model before I build the submarine. And so, the submarine, I'm going to need to hire a bunch of welders and buy a bunch of steel and pay, lots and lots of money. My model submarine, I can just fire up a 3D printer and have that thing out the door in, a couple hours. So anyway, VM, I have the following information. Let's say I'm going to use for my model a fluid velocity of 180 feet per second. And so basically I'm going to be using a wind tunnel. This kind of velocity with water would be absolutely ridiculous. But let's say I want to use air instead. I can use a wind tunnel with air at 180 feet per second. But let's say rho of the model is just equal to the density of air. Then I will also say L of the model is, that's just going to be 1/15th scale. And let's say that the rho density of the fluid for the prototype is going to be the density of seawater. And the length of the prototype is going to be 15 times the length of the model. So I don't actually know the length of the model. I'm not told it. All I know is that it's 1/15th scale. So let's see how this works. Well, solution. Oh, what do you want to find? Find VP, the velocity of the prototype, the equivalent velocity, using Reynolds number similitude. Using Reynolds number similitude. And we'll be working with Reynolds number a lot in the remainder of the semester. Solution here. I can say that Reynolds number is equal to VL over mu, over nu, VL over nu, as we saw here, VL over nu, and then VL over nu. So from this, I can get that VL over nu for the model must be equal to VL over nu for the prototype. And if I solve this for VP, must be equal to VM LM nu P divided by nu M times LP. Now I can then say that also I can look this up in a table and find the viscosities. VP for seawater is 1.26 times 10 to the negative 5 feet per second squared, or feet squared per second, and this is for seawater. I'll need to finish this on the next slide for seawater. And the viscosity for the model is going to be 1.57 times 10 to the negative 4 feet per second for air. Those are relative viscosities. And so finally, Vp is equal to 180 feet per second times Lm times 1.26 times 10 to the negative 5 feet squared per second divided by 1.57 times 10 to the negative 4 feet squared per second times 15 Lm. So I don't actually know the length of the model, but it's just going to cancel out. And if you run through those numbers, you will find that the velocity of the prototype, the velocity of the real thing, is 0.963 feet per second. And that would be the final answer. All right, questions on any of that? Okay, that'll do it for today. I will put those back up in a second, but that'll do